Okay, we're going to look at the Big Bang today and the work of Edwin Hubble, the work of Henrietta Swan Leavitt, and how we changed our view of what the universe is doing, what it might do, and what it's done before. So, pretty big ideas here, and this is in the cosmology section of the astronomy topic. So, there's Edwin Hubble and his big telescope there, and he was the Astronomer Royal, and there's the Hubble telescope named after him. And now, Edwin Hubble was someone who took two very important pieces of work, used both of them, and made a huge amount of observations, and then came up with a conclusion which completely changed the way we thought about the universe. So, Hubble is famous for these three things, really. Well, maybe most famous for these three things: confirming the existence of galaxies other than the Milky Way. Devised the most commonly used system for classifying galaxies. If you did GCSE astronomy, you'll recognise the tuning fork diagram. And discovered a pattern between the distance of a galaxy and its relative velocity. So relative velocity is something that you would have learnt about when you learnt about the Doppler effect and redshift, blueshift. So in the redshift equation, or in the Doppler effect equation, V is recessional velocity. It's not velocity. Recessional velocity, how fast something is travelling towards or away from us. Okay, so Henrietta Swan Leavitt was famous for looking at variable stars in galaxies and seeing a relationship between them. So we've studied this before when we looked at stars, and this is how we figure out distances to stars. So she looked at variable stars. You can see this zoomed in. So there's three images of the same star. It gradually gets brighter, left to right. And she found a relationship between the time period of when it's at its brightest and when it's at its brightest again, and actually how bright it is. So she did that by looking at variable stars close to us to get the relationship, and then assumed that carried on. So the brighter the star is, this is slightly misleading because normally we'll see magnitude in a negative scale. And this actually, the higher up you go on the y-axis, the brighter it gets. So the brighter it gets, the greater the time period. So the longer between brightest parts. So this time period, you could think of this as being quite long. And then for a dimmer star, the time period would be quite short. Okay, so it's over a number of days that this happens. That was the work of Henrietta Swan Leavitt. So if we found a variable star in a galaxy, we could just observe it, plot this little graph, figure out how long it was between when it's at its brightest and when it's at its brightest again. That's the time period. Plot up, plot across, and that would give us the absolute magnitude of its brightest point. So we know how bright it actually is. Okay. So those are used as what we call standard candles. Hopefully you've come across that phrase before. Something where the luminosity is known. So here's a bit of a messy thing here, which we would have seen before. So if the apparent magnitude, how bright it appears, is just simple observation. You just take that. The absolute magnitude is calculated from Henrietta Swan Leavitt's approach, which is figuring out, finding a variable star in the galaxy and figuring out how long it is between bright points, and then you can work out its absolute magnitude from that. So if we've got the absolute magnitude and the apparent magnitude, then the only thing left is to work out D. So Henrietta Swan Leavitt's work gave us the ability to calculate how far away galaxies were as long as we found a variable star in them. They're called Cepheid variable stars because they were first studied in the constellation Cepheus, but yeah, you get variable stars in most galaxies. So that's that's the distance covered. So we now know how to figure out the distance. Before that, it was only the parallax method that we had, and that only worked for close-up objects. Okay, so Edwin Hubble combined these two pieces of work. This is from a previous lesson. This is the Doppler effect. This is the Doppler effect equation. And this is Henrietta Swan Leavitt's work. So, Edwin Hubble decided to look at galaxies And now this is mentioned at GCSE as well. It's very important that you don't start talking about stars. It's all about galaxies. He observed galaxies and he used these two approaches to get some information about the galaxies. So what he was able to do was work out how bright the star was from this, which gave him the ability to work out the distance from this equation. So we knew the distance comes out in parsecs, and then using this he was able to observe absorption lines and see how much they've been shifted. So that's your change in wavelength, divide it by what the wavelength would be in the lab, multiply that ratio by the speed of light, and he had the recessional velocity. So using the Doppler effect equation, he was able to work out the recessional velocity, and using Henrietta Swan-Leavitt's work of the period luminosity law, he was able to get the distance. So he was comparing the recessional velocity to distance. Okay, now he expected it to be not much going on really. Now and again some moving a bit towards us, moving a bit away from us, but we were expecting a pretty static universe, and that's absolutely not what he saw. So this is data from 1929, and you can notice here actually 0 means not moving towards us or away from us. And if you look up close, there's a few anomalies to the pattern here, and we've got our local group of galaxies, so there's not a great pattern going on there. This little one here is Andromeda. So with a negative indicates on this graph moving towards us. So you've got this moving towards us, but then as you look further out at much more galaxies, you'll start to see that there's a trend, and they all start to be moving away from us. And the pattern is the further out you go, the faster they're moving away from us. The bigger the recessional velocity, essentially, kilometers per second. Okay, but one of the issues with Hubble's law and Hubble's work is that it's not an obvious line of best fit. There's a clear pattern, but it's not easy to know exactly where to put the line. But the gradient of this is the recessional velocity divided by the distance, and we go into megaparsecs for Hubble's law, which is a bit frustrating because with the equation with absolute and apparent magnitude we've gone in parsecs, and now all of a sudden we're in megaparsecs. And sometimes the question will give you the information in light years, so you need to convert them, be aware. So yeah, this gradient is something called the Hubble constant. So it's the recessional velocity divided by the distance. How fast something travels away from us compared to how far away it is. Or in other words, what the increase in recessional velocity is for a certain increase in megaparsecs. Okay, so if you think about going from 1 to 2 here and drawing a triangle, you can see there's an increase in recessional velocity compared to an increase in 1 megaparsec there. Okay, and there it is, expanded out. So we started to get a clearer view as we looked at further out galaxies. Okay, so there's different values for what we call the Hubble constant, which is the gradient of that graph, somewhere in between those two lines, I would say. And Hubble's law came to us from that. So Hubble's law just talks about this gradient here, and it's this. So your recessional velocity equals the Hubble constant multiplied by d. But if you look back at the graph, it's just v over d is your gradient. So rearrange this, v over d equals h. So h is the Hubble constant, it's your gradient. You'll see a value on your data sheet, which I think they use 65, which is kilometers per second per megaparsec. So it does lead itself to unit conversion this. The questions aren't too tricky as long as you're confident going from kilometers per second into meters per second, and then going from megaparsecs into parsecs. Okay, so that's the work of Edwin Hubble. There we go. Now, if you look at the units here, you've got velocity over distance is your Hubble constant. So meters per second divided by meters, well then your meters would cancel, which just leaves you as 1 over seconds. So the Hubble constant is in the units of seconds to the -1. Now, what does that represent? Actually, believe it or not, it can be used to calculate the age of the universe. It's, if you've got 65, then it's not just 1 over 65, unfortunately, because you need to convert to seconds or minutes or years. And of course, it's in kilometers per second per megaparsec. So you'll notice that kilometers doesn't actually cancel out with megaparsecs, even though they're both units of distance. So what you'd have to do is either convert the kilometers into the megaparsecs or convert the megaparsecs into kilometers. So if you find that ratio of how many kilometers there are in a megaparsec, which is a bit of a long-winded thing, you would find how many megaparsecs there are in a parsec. Then you'd need to find how many meters there are in a megaparsec, I suppose, and then convert from there and go into kilometers. So that's the tricky thing, and that will take some time to get your head around. But if you do that and you convert, and then you convert it all, so your kilometers cancel out with the kilometers, and then you just do 1 over your answer, and that gives you the age of the universe, believe it or not. So that's something that you should try. And obviously we're looking at 14 billion years approximately. So if it comes out at that, you come out in seconds, so convert it up to years, and then you've done the right thing there. But yeah, that was the way that we've calculated the age of the universe. Okay, so Andromeda is our just a little bit of information. Andromeda is our closest galaxy, and it's actually travelling towards us. So that would show a blue shift, but the vast majority of other galaxies redshift. At GCSE, you kind of learned the phrase that Hubble looked at all the galaxies, and they all showed a redshift, which is nearly true. Right, and I will swap to this now, which is also a recap of GCSE. So when Hubble figured out that all the galaxies were travelling away from us, he came up with the theory that the universe must be expanding. You can't have everything travelling away from you and not be in some sort of explosion. It wouldn't make sense. Unless we were at the centre of the universe and we had some anti-gravity thing going on, which is not the case. So the Hubble's work led to this theory of the Big Bang. Everything's travelling away from us, that suggests an explosion. So if you wind time backwards, it suggests everything was in the middle somewhere, and it's expanded out. But that theory of the Big Bang was clinging to Hubble's work. Hubble's data was the only evidence we had for this theory. And then along came cosmic microwave background radiation. Now these two people pictured here are Wilson and Penzias, and their name is forever linked to cosmic microwave background radiation. So, quick kind of look here. This is the image of the Earth, and here's an image of our solar system. Could we take a photo of the solar system? Yeah, we could from Earth. Here you go. You've got a few of them in there, but on the whole, typically, they'd be tiny dots, not what you see in your textbooks. Here's the solar interstellar neighborhood. We've zoomed out here, and there's Vega. See, looks a bit like that. Well, there's Alpha Centauri. Milky Way? That's not it. Because we've never took a photograph of the Milky Way. Well, we can if we get images of galaxies that we think are similar to the Milky Way, but we've never sent something to take a photograph from the Milky Way outside of it. We could take a photograph from the inside of it, but never from the outside. Local galactic group, here we are, is the Milky Way. Down here you've got Andromeda. So we zoomed out again. And down here you've got Triangulum Galaxy. They're the major galaxies. From the southern hemisphere you can see the small and large Magellanic Clouds. There's a bunch of dwarf galaxies. There's Andromeda. Look at the Triangulum Galaxy. Oh, that pleases me, that image. Alright, so then we go on to zooming out again. This is the Virgo supercluster. So our local galactic group that we've just had a look at is just here. Zoomed out again. There's the Virgo cluster, which to the naked eye would just look like a dot. Isn't that mad? You look like a dot and you're actually looking at a cluster of galaxies. And now we've zoomed out again. So what was our Virgo supercluster? We've zoomed out again. The Virgo supercluster is just here. Good grief. So what have we got now? Look at this Sculptor supercluster. There it is. Oh, it's a dot. So actually, if you found the Sculptor supercluster in the night sky, most people would say, oh, look at that little star. And then no, it's a cluster of a cluster of galaxies. If that makes sense. And then your head just melts with this, doesn't it? All right. And then we zoom out again, and we get to the observable universe, which essentially an artist's impression is just asking a child to put a bunch of dots on, I suppose. But there you go, the Virgo supercluster. Local superclusters just goes to a little dot there. In general, I don't know, about somewhere between 100 and 400 billion stars in our galaxy. And then if there's about the same number of galaxies in our universe. You can think of it as that, as a cheat for a quick way to get how many stars there are in the universe. And then you can guess how many planets. I don't know, times it by 10, 5, whatever you want. There we go. So that's the observable universe. Have we ever taken an image of the observable universe? Well, we can't go outside it to get an image of it, but that's the image from the inside. Very famous image. So, obviously, if we take a visible light image, it's just a bunch of stars, and you know, so what you could do is you could send something out in space, and you could take a panoramic image, looking up, down, left to right, move it around, and link all those images together, and you get this panoramic view. Imagine, though, getting an image of the room that you're sitting in. So if you took a panoramic view, some sort of camera, and then moved it around, so it took in the floor, the ceiling, all the walls, it would be quite hard to pin it onto a flat image of a rectangular image. It wouldn't quite work that simply. So imagine kind of looking from inside. What you'd have to do is stick the images, you know, to some sort of sphere that you had to go inside, which is how, you know, a planetarium works. But here they've kind of done it here, but it's their best attempt at getting it flat. But this is what you would see. So what they've done is they've looked at a very specific frequency, which we'll talk about now. So this is Wilson and Penzias. Wilson and Penzias were asked to build a horn antenna to pick up signals from this. This is like an early satellite. What they wanted to do was send information up, bounce it off this, it would bounce back down, and Wilson and Penzias would pick it up with their horn antenna. But they turned on their horn antenna before any signals were being sent, and they heard a bunch of noise, which was frustrating them. They took it apart, they cleaned it out. I think there were some pigeons living in there, which they moved to a new home, I believe. And they still heard this constant noise from every direction in the sky. They were hearing this noise. So at the same time, this is an incredible coincidence. At the same time, there were 3 people working at Princeton who'd come up with a theory. And we won't get too bogged down into the theory. You always hear this very basic explanation. The theory was that when the universe first became opaque, and some of the energy could travel through it, the heat rays, there was an incredible amount of heat. Now, as the heat has travelled out, the theory is that the universe has expanded. So instead of the heat waves just going from A to B, what happened to them is they've stretched as the universe has expanded. And by clever calculation, they worked out what frequency they will have stretched into. So if you stretch a heat ray or an infrared ray, you increase its wavelength, and you can move it all the way into the microwave region. So that's been redshifted. And they worked out the exact frequency of microwaves that they would expect it to be. And they were preparing to search for it. And they needed something that looked a bit like this. So they figured out that the noise that Wilson and Penzias could hear was the stuff that they were about to search for, which was this leftover noise from the Big Bang, essentially heat rays from the Big Bang that have been redshifted into microwaves. So, it's visible or it's detectable from every direction in the universe, and it's this constant noise that we get, which is the leftover heat from the Big Bang. It's called cosmic microwave background radiation. But they came up with that theory based on the work of the Big Bang. Now, it's really good evidence when you use a theory to predict something and then go out and search for what you've predicted and find it. That's really good evidence for a theory. So there it was. In 1989, we sent up COBE, Cosmic Background Explorer, and got this image. This is the cosmic microwave background radiation. So some places you detect more of it, some places less, and they've color-coded it. 2001, we sent up WMAP, Wilson Microwave Anisotropy Probe, and we got that image, getting a bit more resolution there. And then in 2009, we sent up Planck and got that image. I believe that wispy thing in the middle is the Milky Way, which can be removed from a lot of these images. But I suppose the surprising thing was that it wasn't uniform. So the Big Bang sent out energy and matter not the same amount in all directions, which doesn't seem to link with conservation of momentum, conservation of laws of conservation of matter, lepton number, baryon number, which is matter and antimatter. So more matter was produced than antimatter, and it wasn't distributed evenly in all directions. So that suggests that the Big Bang didn't follow the laws of physics, which is a pretty big deal, I suppose, and one of the arguments against the Big Bang. Are the laws of physics, do they have to work all the time? I think, yes, they do. That's one of the things that physics likes to say. But throughout history, have the laws of physics changed? Were the laws of physics different for the Big Bang? Big, unanswerable questions at the moment, we would think. But there you go. Yeah, so that's the cosmic microwave background radiation. And that is the second bit of evidence after Hubble's work for the Big Bang. Okay, so yeah, you get asked some questions about Hubble's work, but the majority of the questions based on this will be calculations based on Hubble's law, which is what this work will link to. Okay, I hope that was helpful. Thank you very much.